So now that we have imported the project and tried it, we need to actually start task one, which is the translation. But for the translation, we really need to know how our feature models internally represented. So usually the structures that we want to translate, to analyze them, they need to be in some format that the computer can understand. This format is usually called an abstract syntax format. So the way that we write it down is a concrete syntax. So we had here this example where we have this print example. If we run this, we see that this is a concrete concrete syntax representation of the feature model, where we list the features. Then car is a feature which has motor and comfort as children. Motor has the child feature gasoline or electric. And this would be a textual representation of the feature model. Now, this one would be a graphical representation of the feature model, but it's missing the cross-tree constraints. So you could imagine that would also be there for graphical representations. So these are different concrete syntax representations of the feature model, but what we maybe should be interested in is how are they internally in the computer system, in the program that we're going to extend. How are feature models represented there in memory? And that's usually the abstract syntax representation. So in the abstract syntax representation, we see what elements do feature models have. So here in this package, FM, we have the representation for feature models. Let me just put this maybe here on the side that I can illustrate it as we go. So it's an object-oriented representation of feature models. We have a class feature model. The main important thing of the feature model is that it has a root, which is a feature, and it has a list of cross-tree constraints. And that's the feature model, right? So here, the root feature would be this car. Feature model would be the whole structure that contains the root and the cross-tree constraints. We can also, maybe because it's simpler, quickly have a look what are cross-tree constraints. A cross-tree constraint, we have two types, either requires or excludes. Then a cross-tree constraint has a left side, then this kind, it's either requires or includes, and a right side. And those are features. So the left and right of a cross-tree constraint are features, and that's basically it. We have some constructor to make it a little bit more convenient of constructing cross-tree constraints. And then the one that we didn't look at yet is the feature, but the feature is also not very complicated. So the first thing that a feature has is it has a name. Then a feature can be mandatory or not. And a feature can have children, which are again features. And here we did some simplification where we say that we can set child group kinds. And the child group kind, by default, it's none. So car has the child group kind none. So these children are not in any group. But there are other group kinds. There's the OR group, which would be the children of comfort would be in an OR group. And then there's an XOR group, where here in this example, the children of motor would be in an XOR group, right? So these are the different kind of groupings. Usually these groups, they could be, you could have multiple groups under one feature. In our simplified abstract syntax, we only have this one group, which either is none or XOR. So that makes the translation slightly easier, but I think in all the examples that we've seen, this is anyways how it was. So yeah, that's the data representation. Now, how is this stuff instantiated? We can see some class here called example feature model creator. So this is now purely created for illustration purposes. And so it has nothing to do with how feature models are presented. This was all in this package, and that was all we needed to instantiate feature models. Now, this is the code that actually does instantiate a feature model. So here in this line, we're basically creating a feature model. Then we're creating a feature car, and we set it as the root of the feature model. Then we're creating a motor. So there's some convenience method at child where we say the feature name should be motor, and it should be a mandatory feature. So you see here, yeah, the motor is mandatory. And then this adds the child feature to the car and also gives us a reference to that feature so that later we could, for example, add more children to the motor. So here we are setting the child group kind exclusive OR for the motor. This means that all the children of motor will be exclusive ORs. And then we do add child gasoline, that's this one, and add child electric, that's this one. Here again, we get electric because later we want to use the feature electric in a cross-tree constraint. But that's basically how we build also this other side with the comfort feature. Here you see it's an optional one because we simply set the flag here to false. And we also set the mandatory to false for all the children that are in XOR or OR groups. Right now, there's nothing that checks this. So usually you would have well-formedness checkers that would make sure that your abstract syntax that you instantiate is well-formed, so really represents a feature model. Here, we just have to trust that people will only instantiate these in a way that they represent valid feature models. But you could imagine that we could, of course, check this, that groups, unless they are none, they always have mandatory set to false, things like that, right? Now, the way we do cross-tree constraints, very simple. We say, we construct a new cross-tree constraint. We say electric requires heating. So if we have an electric motor, it requires that we also have the heating feature included in our car. And then we add this as a constraint to the feature model. And that's it. This creates the feature model in abstract syntax that we see here and that we see here. So if you want to know how to transform an instance of feature model to this text, you could simply have a look at this class printer example, because that's what it does. When we execute the printer example, it will print this. And how does it do it? It asks the feature model creator to get the simple feature model. That's the code we just looked at. And then it prints it. So if we would, instead of get simple feature model, there is also one which is called bad feature model, and we can maybe see or guess why it is bad. So let's run this now and print the bad feature model. The bad feature model has a car as the root. The root has a child motor, which is a mandatory child, so very much still like this. But that's about everything in this feature model, except for a cross-tree constraint that says if you include a motor, you need to exclude a car. So including the motor excludes the car, which, as you can maybe guess, makes this feature model inconsistent. There's no way to define a product, so you only have two possible features, right? If the car is the root, so you always need to have a car, but then it says if you have a car, then it's also mandatory to have a motor. But then if you have a motor, you can't have a car, so there's a contradiction here. So this is an inconsistent feature model. So let's change it back to the more to the larger one, and then see how actually these ones are printed. So the first thing method we call is print feature model, which prints the features in the feature model by starting from the root, and then prints the cross-tree constraints. So cross-tree constraints, we simply iterate in a for loop over the cross-tree constraints and preprint the name plus the kind plus the name of the right side, right? So left feature name, kind of the cross-tree constraint, and write feature name. So if you recall, for this simple feature model here, we had electric requires heating. So the left feature was the electric feature, the right feature is the heating feature, and the kind is requires. Now, how do we print the features? That's more interesting because the features are actually a tree. So what's going on here is that we start by printing the root in this print feature. And then for every feature, we print this line here that says, this is the feature with this name. It is mandatory or not, or optional, right? And then we print the children. So this printing of the children is something that is done here. We first say how many children there are, and then we iterate over the children. Here we just analyze which group do we have. Do we have the XOR or OR group? Then we print it, like in this thing here that's printed from the child group kind and then the dash group. And here we have the for loop that iterates over the children. And then for each child, it prints the feature again. So you see there's this recursion where we first called this for the root, we printed some general information, and then we call the print feature also for every child until there are no features anymore in the tree. So this means then we have printed all of them. One thing, this indent here, we use it just to do this indentation where on the first level we didn't do any indentation. As you could see here where we said print feature root, no indentation. That's why it's all the way to the left. And then we are starting to build up an indentation for every further call of print feature here by saying print child info. We're already indenting the children a bit. And then next time we print a feature, this adds again some further indentation for the next children. So that's why here the car is on the leftmost level. Motors, because they're on the next level here, they're indented by a little bit. And then the gasoline electric, they are indented twice as much because they are one level further down. So that's how we can go over the abstract syntax representation of the feature model and print information. And if you have a look at the task in the worksheet, that's basically slightly different, but you will see that there are some parallels. So the first task would be to implement this translate formula method, which takes as input a feature model and then produces a formula in Limbool format, just like we did in the exercise. So this is in the feature model translator class. The feature model translator class is here. Right now, you see that the translation is really empty. But why is this important? Where is this used? This is used in the feature model analyzer. The feature model analyzer can do things like checking consistency of a feature model, checking for dead features, and checking for mandatory features. So how does it check consistency? Well, that's very simple. It takes the feature model, translates it to a formula, passes the formula to Limbool, executes it, and if it's unsatisfiable, then it means that this feature model is not consistent. So we return false. If the formula that we generated is satisfiable, which means that there is some product that can be configured from the feature model, then we would return true. So if we try to execute the check consistency, what's going to happen is that it will fail because right now the formula that we're getting is independent of the feature model, some simple unsatisfiable formula. So this check here, you can, if you want to invoke the feature model analyzer, check consistency for some feature model. The maybe best way to do this is using test cases. So you will see that there are some JUnit test cases here in the source test Java, and then in the corresponding package, we have two methods that are called test check consistency. One of the car feature model, that's the one we have always been looking at, and the other one of this bad feature model. So the car feature model, yeah, if we look at it again, you can probably guess that it is consistent. We could, for example, have a car, then we need a motor, and then maybe we take a gasoline engine. So comfort is then optional. The cross-tree constraint, electric requires heating, is not valid because we didn't pick electric. So one possible product here is car, motor, gasoline. And that's why we're expecting that this thing should return true. And for the bad feature model, we know that it doesn't have any products, so we're expecting that it returns false. So if we want to run all these JUnit tests, we can, for example, click on the file or the class and say run as JUnit test. And we see that the tests fail because the reason is mainly because this code is missing that actually translates the feature model to a formula, right? Now it always gives an unsatisfiable formula. So what you need to do in task 1 is take this feature model right here and add the code that translates it to a formula that represents the semantics of the feature model. So you can follow the rules in this table and also look back at the exercise that we did in the previous session.